With the decimation of oysters over the past century, efforts to replenish wild stocks have increased. At Valdosta State University, undergraduate students working with Dr. Thomas Manning from the chemistry department have been developing a technology to contribute to these efforts. We currently have special activity licenses to conduct this research in Apalachicola Bay, Florida, but we would like the opportunity to apply this technology along the Georgia coast.
Oysters do not only serve as a food source. Oyster beds are imperative in preventing coastal erosion. Coastlines along the United States, particularly in Louisiana, are disappearing at an alarming rate due to the loss of these oyster reefs. Oysters also play a critical role in improving water quality. A single adult oyster is capable of filtering up to 50 gallons of water per day. This technology is aimed towards replenishing wild diploid oyster stocks. Depicted here are some of our materials soaking in a runway at the FSU Marine Lab before being deployed near a natural oyster reef to collect spat.
This technology is based on three different aspects: a modular design allowing greater flexibility with placement areas, as well as the ability to transport materials, using nutrient-enriched cellulose to accelerate microbial growth and serve as a carbon source, and using a nutrient-enriched cement with a more neutral pH that will biodegrade over time.
Treating the cellulose and concrete with a variety of nutrients such as vitamins, amino acids, and sugars allows microbial growth to occur at a faster rate, therefore improving colonization of the surface by sessile invertebrates. In the Gulf Coast, our materials have shown wild diploid oysters reaching market size in 13 months.
There are several different geometries that can be constructed using cellulose and concrete. The design can be altered according to local currents, ocean terrain, and tides. They are also designed in smaller modular units as opposed to one large structure, so that the units can be easily retrieved and/or moved to another location if necessary.
Selectivity of biofilms grown is a function of the structure's surface chemistry. The picture on the left depicts a biofilm grown on the cellulose structure. This biofilm has been collected for testing as depicted in the picture on the upper right. On the bottom right, a scanning electron microscope image shows bacteria grown on our materials. These biofilms are important for oyster larvae, coral larvae, sponges, and other invertebrates.
A simple example of how this system may work is that the small modular structures are placed near an existing oyster bar. Once the spat is released into the water column, the modular reefs will be in place to serve as a colonization surface.
The advantages to this design are small modular units that can easily be moved to other locations. They may then be transported to other areas to begin replenishing oyster stocks where reefs have been lost for restoration purposes. This technology is based off of the EPA's 12 Principles of Green Chemistry, meaning that it's safe for the environment and will biodegrade over time, leaving behind a thriving ecosystem.
This research has received national and international press through publications in Sport Diver magazine and Clean Technology Business Review. This technology was also evaluated by the National Science Foundation's I-Corps program, aimed at determining whether research conducted in the lab can be commercialized. VSU was one of 24 teams chosen across the country to participate and was one of 6 that had NSF support for further commercialization. Thank you for your time, and please contact us if there is any interest in collaborating.